All right, let's dive into the animal kingdom. We're going to piece together a blueprint for life itself and, uncover the simple but brilliant rules scientists use to make sense of all the incredible diversity on our planet. So, let's just start with the biggest question right off the bat. How do you possibly organize a kingdom with over 1 million known species? It's like tackling the world's most gigantic, most complex puzzle. But today, we're going to find the key. Okay, so our blueprint has to start at the most fundamental level, right? We're going from cells to systems, looking at the absolute basic building blocks of every single animal out there.
Think of it like you're building with Legos. You could just have a loose pile of bricks. That's the cellular level, kind of like what you see in sponges. Or you could start grouping similar bricks together to form walls. That's the tissue level, like in a hydra. Then you can combine those walls to make a room, which is the organ level, like in flatworms. And finally, you connect all the rooms with hallways and wiring to create a fully functioning house. And that's the organ system level, the complex design used by pretty much everything from insects to us.
So once you have your building materials, you need a basic layout, a floor plan. The simplest one is the blind sack plan. Seriously, just imagine a sock puppet. It's got one opening. That's exactly how animals like flatworms work. One hole is both the mouth and, well, the exit. But the more advanced layout, and this was a huge deal, is the tube within a tube plan. This is a complete digestive tract with a separate mouth and anus. Think of it like a super efficient assembly line. Food goes in one end, waste comes out the other. It's an incredible design used by almost all advanced animals, including us.
Next up, let's zoom out a little and look at the overall blueprint for the body itself, focusing specifically on its symmetry and its layers.
Now, what's really fascinating here is how an animal's shape is tied to its lifestyle. Some sponges are asymmetric. There's no real plan. They just kind of grow. Then you have animals with radial symmetry, like a starfish. You can slice them through the center, like a pizza, any way you want, and you get two identical halves. This is perfect for creatures that just sit there or drift around, because it lets them catch food from any direction. But most of the animals we know, including us, have bilateral symmetry. There's only one way to slice us right down the middle to get two mirror image halves. This design is fantastic for moving with purpose, giving you a distinct front end that encounters the world first.
Okay, so during development, an embryo forms these layers that are destined to become all its different parts. Simpler animals, like jellyfish, are diploblastic. They have just two layers, an outer ectoderm and an inner endoderm. But the big evolutionary leap was becoming triploblastic, which introduced a third middle layer called the mesoderm. And let me tell you, the mesoderm is the true game changer. This is the layer that develops into muscle, bone, and all the complex organs, all the machinery that allows animals to move, hunt, and build really complex bodies.
Now that we have the layers, we need to talk about the internal architecture. This brings us to Section 3, the space within, where we're going to get a handle on this thing called the colon.
So, what exactly is a colon? Well, it's a fluid-filled space between the body wall and the gut. But here's the absolutely crucial detail. A true colon is completely lined by that middle layer, the mesoderm. This cavity is so important. It gives organs room to grow, it cushions them from bumps, and it helps circulate fluids. It's a key innovation.
And this is how that one concept helps us classify whole groups of animals. You've got your acoelomates, like flatworms, which have no body cavity at all. They're basically solid inside. Then you have the pseudocoelomates, like roundworms. They have a cavity, but it's not fully lined by the mesoderm. It's kind of like a partially finished room. And then you have us, the coelomates, from earthworms all the way to humans. We have that true, fully lined body cavity, which allows for the most complex arrangement and support of all our internal organs.
We've built the structure, so now it's time to install all the internal systems. You know, the pipes, the pumps, and the wires.
How does an animal move all the important stuff like nutrients and oxygen around? Well, there are two main models. Open circulation is kind of like a flooded plain. Blood just flows freely inside the body, directly washing over all the tissues. It's pretty common in invertebrates. In contrast, closed circulation, which we have, is like an incredibly efficient highway network. Blood is always contained inside vessels, arteries, veins, capillaries, which allows for much faster and more targeted delivery. This system is a must-have for active animals.
And what about the command center, the nervous system? Here you can see a really clear progression in complexity over time. It starts with a simple, diffuse nerve net, like what you'd find in a hydra. Then it evolves into a more organized, ganglionated system, like an earthworm's ladder-like setup. And finally, we get to the central nervous system of vertebrates, a powerful central processor with a brain and a spinal cord.
For our final section, let's hit a few of the absolute key evolutionary milestones. These are the features that created the major branches on the whole family tree.
First up is the notochord. It's this flexible rod that provides skeletal support in an embryo. And having a notochord at some point in your life is the single defining feature of our own group, the phylum Chordata. It's a really big deal.
You hear this saying all the time in biology. All vertebrates are chordates, but not all chordates are vertebrates. So what does that actually mean? Well, it means that the notochord is the foundational structure. In animals like us, the vertebrates, that notochord develops into our vertebral column, our backbone. But some chordates keep that simple notochord their whole lives and never ever develop a backbone.
Next up, temperature control. Cold-blooded animals let their body temperature just go with the flow of the environment, which saves a ton of energy. On the flip side, warm-blooded animals like birds and mammals burn a huge amount of energy to keep their internal temperature constant. But the big payoff is that they can stay active in a much wider range of climates.
And finally, how does an animal grow up? In direct development, the young simply looks like a miniature version of the adult, like with humans or birds. Pretty straightforward. But in indirect development, you have this larval stage that looks completely different from the adult. Just think of a tadpole and a frog, or a caterpillar and a butterfly. These animals have to go through a mind-blowing transformation called metamorphosis to reach their final adult form.
So, when you put this all together, what's the big takeaway? These criteria, the body plans, the symmetry, the internal systems, they aren't just a list of terms to memorize for a test. They are the story of evolution's choices. Each one represents a key decision, a major innovation that literally built the entire animal kingdom, from the simplest sponge all the way to the most complex mammal.
And that brings us to one last thought. We've just mapped out the architectural rules that built the animal kingdom as we know it today. But evolution never stops. So the real question is, what rules will build